De Moivre's theorem. Now, De Moivre's theorem is the continuation of complex numbers, which we have already discussed in the previous session. Now, what is the significance of De Moivre's theorem? Before we discuss the theorem in brief, it is very important to understand the significance of De Moivre's theorem in the branch of mathematics. Now, De Moivre's theorem helps us in finding the roots of complex numbers. So it is used in finding the nth roots, especially in finding the nth roots of unity, is one of the most significant part of the De Moivre's theorem. Now let's see how we can find the nth roots of unity using the De Moivre's theorem, or how we can find the nth roots of the complex number using De Moivre's theorem. Now initially, to start with, an integral index, that is, when n is an integer, we have an exclusive De Moivre's theorem. So let's see what is De Moivre's theorem for an integral index, the index being an integer. So here, for theta being a real number and n being an integer, for theta belonging to R and n belonging to Z, we have cos theta plus I sin theta whole power n is cos n theta plus I sin n theta. Is how we have De Moivre's theorem for an integral index, because cos theta plus I sin theta is a complex number when raised to an integral or an integer n gives me directly the integer, the index comes to the base of the angle as cos n theta plus I sin n theta for this. And note, since cos theta plus I sin theta is referred as cis theta in the short form, therefore my De Moivre's theorem can be split as cis power n theta is cis n theta, is how we understand the De Moivre's theorem for a rational index in a shortcut form as cis power n theta is cis n theta, which is nothing but same as this equals this. Now that we have discussed about De Moivre's theorem for an integral index, now comes the question, what if the index is rational, which is not an integer? So let's see how the theorem is stated for a rational index, n belonging to Q. So for theta belonging to real numbers and n belonging to rational numbers, my De Moivre's theorem says that cos theta plus I sin theta whole power n has one of the values as cos n theta plus I sin n theta, but not exactly equal, but this has one of its value as cos n theta plus I sin n theta, is how we conclude for n belonging to Q in the form P by Q. Now let's define the nth root of a complex number, because this plays a vital role in De Moivre's theorem. The whole of De Moivre's theorem is about finding the nth roots of a complex number. Therefore, it is very essential that we define nth root of a complex number and then connect this with De Moivre's theorem. So in order for this, let me consider n belonging to z plus, or n is a positive integer, and z0, which is not equal to 0, is a given complex number. then such that z power n equal to z naught such that this equal to this, that implies z equal to nth root of z naught or z naught power 1 by n is called nth root of z naught, is how we understand nth root of a complex number. So z equal to this implies it's a nth root of a complex number. Now let's find the formula for nth root of a complex number. So any given complex number, I can find the nth roots of that complex number using the formula which we are going to discuss now. That is, for theta belonging to real numbers and n belonging to z plus, if my complex number z is r times cos theta plus I sin theta, then for this, that implies the nth roots of z are given by, of complex number z, are given by r power 1 by n of cos theta plus 2k pi by n plus I sin theta plus 2k pi by n, is how we derive the formula of nth roots of a complex number z, where k is set to run from 0, 1, 2 till n minus 1, is how we understand the nth roots of a complex number for k running from 0 to n minus 1. So each of this denoted by ak is given by a0, a1, a2, a3 till an minus 1, which are nth roots depending on each of k. Each of k defines each of the complex number with that respect to k substituted here. So this is denoted with ak and k running from 0 to n minus 1, the nth roots of a complex number z. And also note that for each of k, you have each of ak, that is, for k equal to 0, 1, 2, 3 till n minus 1, I have nth roots of z, which are a0 for k equal to 0, then a1, a2 till an minus 1 are all distinct. All ak's are distinct, that is, they are not going to coincide, is how we need to understand the distinct property of each of the nth roots of z. Secondly, I find that one of ak coincides with actual z. So every complex number coincides with one of its nth root, is how we understand the second property. That is, one of ak coincides with z, is how we get the nth roots of a complex number connected with these two basic properties. One is all ak's are distinct, and the other is one of ak coincides with z. Now let's derive the formula for nth roots of unity. Now that we have discussed about nth roots of a complex number, let's define the formula for nth roots of unity. So in this case, if I take z power n equal to 1, that implies the complex number z written in the form 1 power 1 by 1 is called nth roots of unity. So in this case, we have, say for example, for theta belonging to r and n belonging to z plus, such that n is greater than 1, then in this case I have let omega equals cos 2 pi by n plus I sine 2 pi by n. Now this omega will decide all the nth roots of unity, because if omega is cos 2 pi by n plus I sine 2 pi by n, that implies 1 omega square, omega cube, and omega power n are called distinct nth roots of unity, is how we understand nth roots of unity are 1 omega square till omega n minus 1, where omega is this. Therefore, if I just connect this with omega is cis 2 pi by n, which is cos 2 pi by n plus I sine 2 pi by n is cis 2 pi by n, then my omega power n is nothing but cis 2n pi by n, which is cis 2 pi, is how we understand, that is 1. So omega power n is 1. That implies omega power n is 1, and 1 plus omega square till omega n minus 1 is 0 are the two basic properties which I identify from nth roots of unity. The first property is omega power n is always 1, and sum of all the nth roots of unity is 0, is how we derive the formula connected with nth roots of unity for a given complex number z, as z power n equal to 1. Now let's consider the complex number r times cos plus I sine in the polar form. Now if I take a unit circle with radius 1, then any point on the unit circle is r theta, but because r is 1 for the unit circle with center as origin and radius is 1, I have this in the form 1 comma theta. Therefore, every complex number can be denoted with a point on the unit circle which makes an angle theta in the positive direction of x-axis. So if I use this concept of the unit circle with radius 1 and every point on unit circle denoted with the polar coordinates r theta, then my nth root of unity, which is given by cos 2k pi by n plus I sine 2k pi by n, would nothing but give me the radius is 1 and theta is 2k pi by n. Therefore, the point P with its respective polar coordinates gives me r theta, that is r and theta, with k running from 0, 1, 2 till n minus 1, is how I get this. So for each of k, I have each of the angle which varies, and hence each of the point on the unit circle depends on the values of k. Every k gives me every point on the unit circle. Say if I have k equal to 0, then 1 0 lies out here, and then etc. proceeding in the manner. Now let's see the nth roots of unity for this given in the geometrical representation of a unit circle. Now that every point on the unit circle is 1 2k pi by n with k running from 0 to n minus 1, my nth roots of unity are obtained when I take n is equal to 8. So my nth roots of unity come when I take n is equal to 8. Therefore, substituting n equal to 8, my first point when I take k equal to 0 is 1 comma 0, which I denote with p naught. Is how I get this. Secondly, when I want to find p1, I take k equal to 1 and 2 pi by 8 is what I get when k is 1. Similarly, I take my p2, which is given by k equal to 2, that is 2k pi or 2 pi. Suppose I fix myself with k equal to 1, 2 pi by 8, which I got here, and then when put n equal to 8, k equal to gives 4 pi by 8, 1 comma 4 pi by 8. Now this is when I put k equal to 0, this is when I put k equal to 1, this is when I put k equal to 2, and then similarly I take p3, which is obtained by taking k equal to 3, 6 pi by 8. Etc. Now this proceeds until I take p8 or p continued taking k equal to 8 gives me the final thing where I take p8, that is 1 comma k equal to 8 gives me 16 pi by 8, which is 2 pi, where the circle ends. So I halt at this point because here the circle ends after going through 360 degrees revolution, and hence I get 8 points on the unit circle, each given by 1 0, 1 pi by 4, 1 pi by 2, 1 3 pi by 4, and so on and so forth until it reaches 1 2 pi, which can be denoted on the unit circle with 8 respective points. Therefore, I obtain my first point p naught is 1 0, p1 is 1 comma k equal to 1, which was pi by 4, and p2, which is 1 and pi by 2, and p3, which is 1 and 3 pi by 4, or this can be written as 2 pi by 4 because I get multiples of 1, 2, 3, and p4, 4 pi by 4, which is pi, p5, 5 pi by 4, p6, 6 pi by 4, and p8, which is 1 8 pi by 4, which is 2 pi. So it ends here because 2 pi is one full rotation of circle. So this is 360 degrees where the circle halts. That is, when I take a unit circle with radius 1 and center as origin, I have my p naught, which is here, my p1, which is here, because 1 pi by 4 is exactly 1 unit from here, and with polar coordinate of pi by 4 is 45 degrees out here. Then this is p2, which is 1 2 pi by 4, and then here comes p3, p4, p5, p6, p7, and this is also p8. Is how we get all the 8 nth roots of unity on the unit circle. So geometrically we understand the nth roots of unity as points on the unit circle, which when joined gives us an 8-sided closed figure, which is called a regular octagon. So this on joining gives us a regular octagon, which is an 8-sided figure which is formed by joining each of the points P0, P1, P2, so on and so forth till P8. The nth roots of unity is nothing but an n-gon. So we conclude nth roots of unity is nothing but a regular n-gon or a polygon on the unit circle. Now in the next concept, we are going to discuss exclusively about cube roots of unity as a special case of nth roots of unity. So when it comes to cube roots of unity, we understand that n is equal to 3. So usually you have x cube equal to 1 implies x is cube root of 1, which you're going to find. And then in this case, we find that the cube roots of unity are 1 minus 1 plus I root 3 by 2 is how we get 3 cube roots of unity, where this is denoted by omega and this with omega square, such that omega cube is 1 and 1 plus omega square is equal to 0 are the two basic properties which we have in cube roots of unity. And also it is very important to note that omega is cis 2 pi by n or 2 pi by 3, through which we construct the given omega and omega square in the mod amplitude form or the polar form as cis 2 pi by 3. So now that we have discussed about cube roots of unity as 1 omega square, which are cube roots of unity, let's see how they are geometrically represented. Now recently we have seen that nth roots of unity are the vertices of a regular pentagon or an n-gon in a unit circle. Therefore, if I take cube roots of unity, n is equal to 3, that implies 1 omega square are the vertices of a trigon, a regular trigon. Now a trigon is nothing but a triangle. Trigon, that is equilateral triangle inscribed in a unit circle of center origin. That is, when I take a unit circle of center origin, then each of omega is cis 2 pi by 3 implies this is 60, which comes out here, which is P0, and 120, and next is 120, which comes here, and then 360 by 3. First it comes with 120 as P0, and then 240, which comes as P1, and then 360, which comes as P2, are joined, which form an equilateral triangle P0, P1, P2. This is P0, this is P1, and this is P2, is how we get P0, P1, P2 forms an equilateral triangle. So therefore P0, P1 and P2 forms an equilateral triangle inscribed in a unit circle with center origin. So cube roots of unity are connected with an equilateral triangle. Now the question comes on how do we find the nth roots of a complex number. As we have discussed the formula for nth roots of a complex number, let's see how we can use that in solving some example problems. If my question here says find the fourth roots of the complex number root 3 plus I. So in order to find the fourth roots of this complex number let's see how we can do that using the connected formula. So in this case, my complex number z written in the form root 3 plus I would like to convert this into the polar form or the mod amplitude form. So in order to do this, my r is root of root 3 whole square plus coefficient of I, which is 1 of 1 square, which on simplification gives me 3 plus 1 is root 4, which is 2. Therefore r is equal to 2 in this case. So let's convert this into mod amplitude form with the value of r, which is 2. Therefore z is 2 times of root 3 by 2 plus I times 1 by 2, which is obtained by this r multiplied and divided for the z. So multiplying and dividing by 2, I get this, which can be written as 2 times. This is root 3 by 2, which can be written as cos 30, because we know that cos 30 is root 3 by 2, plus I sine 30 is how we get. Therefore, z is root 3 plus I, which can be written as 2 cos pi by 6 plus I sine pi by 6 is the mod amplitude form of the given complex number. Therefore, in order to find the fourth roots of unity, I find the fourth roots of z implies z power 1 by 4. Z power 1 by 4 is root 3 plus I power 1 by 4, which is nothing but 2 power 1 by 4 of cis pi by 6 whole power 1 by 4. So this is the one through which I am going to have k equal to 0, 1, 2, 3, and the fourth roots of unity are given by ak as 2 power 1 by 4 cis 2k pi plus theta by n is the formula which we have, where n is 4, k is 0, 1, 2, 3, and theta is pi by 6. So based on these three basic properties, let's see how we can find the fourth roots of unity. So substituting n, k and theta into this, I get each of the values where k equal to 0 implies I get a naught, which is 2 power 1 by 4 of cis pi by 6, which is pi by 24, which I get here. Then I get my a1 when k equal to 0, when k equal to 1, which I get here in the form as 2 power 1 by 4 cis theta, which is pi by 6, and k equal to 1 is 2 pi plus pi by 6 by 4. This on simplification gives cis 6 to 12, 13 pi by 24, and then k equals 2 implies a2 which is 2 power 1 by 4 of sys 2 pi into k, which is 4 pi plus pi by 6 by 4, which on simplification gives 6 4s 24 plus 1, 25 pi by 24, and then finally k equals 3. Last value gives me A3 is 2 power 1 by 4 sys 3 times 2, which is 6 pi plus pi by 6 by 4, that is 6 6 36 plus 1 on LCM gives 37 pi by 24. Therefore, this, and this are called the fourth roots of the given complex number. Z equals root 3 plus I is how we find the nth roots of a complex number by converting into mod amplitude form and then using the respective formula which we have out here. For finding nth roots of unity, this formula is used for r equals 2 is what we get here.